First of all, many thanks to the organizers to have this opportunity to speak here. It's been already quite nice to interact with my colleagues here from far away to talk further about our common interest. This talk has a motivation that is entirely towards the question, what promise do GRBs have for gravitational waves? That's becoming a well-known question with the advanced construction of LIGO, Virgo, and a recently funded Japanese detector, KAHRA, which will be a 3-kilometer gravitational wave detector, very similar in size to Virgo, but with cryogenic technology. And it will be built in the mountain of Kamiokande. So what information can we extract from electromagnetic observations to support the question, or to address the question, what prospects may we have for gamma ray bursters to produce gravitational waves? And my talk will be mainly on long GRBs. Most people think, probably correctly, that short GRBs come from mergers, so that kind of brings in a very natural way a gravitational wave signal. But for long GRBs, the question is a little bit more involved, because it's not clear if they're associated supernovae, maybe luminous gravitational waves, or perhaps if not, some of the long GRBs come from mergers. So the question is much more involved, and you need to pay much more close attention to our existing electromagnetic observations to say something which is potentially sensible in that direction. So I'll talk about a recent development, which is a high-frequency analysis of light curves of Bepo-Sachs. So Bepo-Sachs has been a wonderful instrument, not only because it had 4 detectors very redundantly taking light curves in different directions, but also because of the 2 kilohertz sampling rate. And it's the only catalog that offers this very high sampling rate, or sampling frequency, with which you can look for signatures up to 1 kilohertz. That looks like a crazy thing to do if you think about what it means looking at gamma ray light curves with a sampling rate of 500 microseconds, where typically, the maximum number of photons in such a bin is at most 20. And many times it's just 0. So these are very non-trivial, highly discretized light curves. And the question is, can you get something sensible out of it? But just to fix ideas, let's start with something very basic that literally fits on a postcard. Already in 1964, the basic instrument, or instruments, Vela and Conus, of discovery of GRBs. And as you know, in 1967, a posteriori, it was discovered in the archive that there was this mysterious transient that we now have learned are extragalactic gamma ray bursters. So the first major throughput, or the major advance in this business was, of course, Betsy, that provided us tremendous statistics on these events. And the next breakthrough came from Bepo-Sachs, which identified through the associated X-ray afterglows that provided sufficient accurate pointing that these actually have, if you wish, a familiar astronomical origin in terms of a host galaxy. And later on, we realized that they come with massive stars, at least the ones that are known as long GRBs, as identified by Betsy. So that gave rise to a huge industry on understanding the specific properties of the associated supernovae. And they're core collapse events coming from massive stars. They're radial loud, they're aspherical, and some of them may even have, or some of them quite generically, even things like 1987A come with jets. And of course, 1987A is important because it gave us first principle evidence from a light curve in relatively high MeV neutrino emission, up to 40 MeV, that matter at supranuclear densities was produced. So these are, by all accounts, genuine core collapse events in the sense that core collapse produced very high density matter. So that will be essential to the rest of my talk. These supernovae are not so trivial. They actually produce relativistic ejecta from the remnant stellar envelope up to and beyond 10% of the velocity of light. So by all means, these can be dubbed relativistic supernovae. And they're also rare, as we've learned to appreciate. Depending on your statistics, you're not going to get more higher event rates than, say, 1% of the type 1 BC parent population. My own estimate was about 0.2 to 0.4%. Other estimates are a little bit more optimistic, up to perhaps 4%. And that by itself, as you know, the 1BCs are not very common either. Depending on your survey, it's either, say, 10% of all supernovae, or perhaps, like in PTF, as I learned in this meeting, it's about 7% of all supernovae. So by all accounts, GRB supernovae are very rare. So they are related to a large degree to supernovae, but not only they are rare, they also do not share the same position statistically in the host galaxy. They're much more centrally located, as we know from work by Fruchter. Now, how often do they actually occur? When you think about, say, LIGO, Virgo, and Carta searches, what you want is events that are not too far. So what we're really interested in is local event rates. One event rate we do actually have, it's about once per 50 years of core collapse supernovae in our own galaxy. That's actually a relatively accurate result from Deal et al. Using the relatively short-lived aluminum 26 in our own galaxy. But 1 per 50 years is certainly not a record holder. There are galaxies like M51, admittedly that's an interacting galaxy, that has core collapse supernovae based on n equals 3 that is more often than once in 10 years. And M82 is similar, that also has an event rate of about once per 10 years. Those are very high event rates. And these kind of galaxies are exactly the type of galaxies that will be of interest to keep track of when you think of searching for gravitational wave candidates in the form of core collapse supernovae. As you may know, they come in two kinds, or at least core collapse supernovae are very diverse. This is two histograms of a table of 56 core collapse supernovae by Maurice et al. And they identified, this has nothing to do with a complete sample of any kind. It's just they had 56 supernovae that are relatively well studied. And the normal, essentially narrow line events show, very roughly a Gaussian distribution. It's not so important that it is Gaussian, but it's sort of a regular distribution. Whereas the broad line events, if you look at the distribution of the ejection velocities, are much more irregular by all accounts. There, of course, this is also a relatively low number. It's about 17 in the broad line region. But more importantly, if you calculate the mean of the ejection velocities of the broad line events, they are higher than the mean of the narrow line events with a level of confidence of 3.9 sigma. So the broad line regions also tend to be more energetic, or at least have higher kinetic velocities. Now, a 64K question is, if you have a core collapse supernova, what does it make? Does it make a neutron star, or does it make a black hole? And 1987A is actually an interesting case because we don't really know the answer. It probably didn't make a neutron star, but real evidence for a black hole we also don't have. But from a gravitational wave perspective, this distinction is very important, because the prospects for gravitational waves associated with making a neutron star are extremely different from the prospects of making gravitational waves if you make a black hole, for a variety of reasons. One reason is that if you think about the relevance of spin energy, then clearly the spin energy has a strong budget limit in the context of making a neutron star, whereas in the case of making a black hole, the potential for spin energy to be associated with gravitational wave emission, as well as making the supernova in the first place, is vastly different. I mean, the rotational energy of a solar mass say 10 solar mass black hole is about 100 times more than the maximal spin energy of a neutron star. Now you can make this a bit more quantitative. There was a paper in 1970 by Bisnawatchi Kogan, who will be here later in this meeting, who discussed this very generic idea of making a supernova out of an angular momentum-rich inner engine. And it's actually a nice model where what you're looking at is the conversion of rotational energy into radial momentum. And this radial momentum is carried off by magnetic wind, and the magnetic wind impacts the stellar envelope from within, and hence by momentum conservation, you'll be pushing out the remnant stellar envelope. So the key question here is, what is the efficiency of this process? Obviously, this is kind of like a gearbox that converts rotation to radial momentum And the efficiency, of course, cannot be 100%. But the key issue is that the efficiency depends on the baryon loading. If you have a magnetic wind that's strongly baryon loaded, you tend to be more efficient than if you have a magnetic wind that is highly deprived of baryons. And so essentially, so you can put this in numbers, and hence you get an upper limit for the kinetic energy in the supernova based on your assumption of the efficiency, given that the rotational energy of your neutron star or proton-neutron star is strongly budget limited. So let's look at a table of events that were tracked by a number of people. So this is extracted from the literature. And for some of them, especially the GRB supernovae, estimates of the kinetic energy in the supernovae have been obtained. Weakly model-dependent, observationally determined. And if you then include, say, your favorite choice of an efficiency, we took a relatively optimistic efficiency of, say, 25%, then you find that for a number of events, for most of the events, the results are indeterminate. You can either produce them by spin down of a neutron star or by spin down somehow of a rotating black hole. But there are two events that stand out. And actually, they happen to be both in 2003. They're very well-known events like 030329. And the other one is 031203. And they have such large amounts of energy in the supernova ejecta that the energy reservoir required to make them, in one case, is about 10 times the maximal rotational energy of a neutron star. And in the other case, it's about 5.3 times. So even if you disagree with my choice of efficiency and you think there are some model dependencies in estimating the true energy and the kinetic energy of the supernova, it's very difficult to reconcile these events, the spin down of a neutron star. They're just too energetic. Okay, then there are peculiar events. And let me just say up front, 060614 is like that. It's a long GRB, which was not too far. And as you know, it has been looked at also by the HST for 15 kiloseconds. That has no identified supernova associated to it, at least not in the normal way that we think we would identify supernova. And then there are a few other ones, like a halo event, 070125, and then there are a few other ones. Okay, there are not that many, but we have a few events that are very difficult to reconcile with either a supernova or a massive star. So what to make of this? You can call them orphan long GRBs. Of course, it doesn't explain anything, but it's a very important issue. Just like what I learned at this meeting, there are GRBs that have extraordinarily long durations. I think those are very important exceptions that provide perhaps clues, if not constraints, to our theoretical understanding.
Just a comment here. The distinction between what we call long and short GRBs is not definite.
I know.
Okay, so
it's a very messy
it's one possible solution that those without the supernovae are actually generated by the same mechanism producing the short GRBs, for which we know that there is no...
That's exactly the direction I wish to go. Then you're looking essentially at my last column that bluntly says merger. Okay, I'm just giving you a thumbnail overview because most of us are very familiar with the history of GRBs, but this overview is geared towards the rest of my presentation. So they are rare, and we have event rates in a few cases that are very well determined, but overall, roughly, we're looking at an event rate perhaps of 1 per year within 100 megaparsec. And many of them, but perhaps not all of them, are associated with core collapse supernovae. And then we have these peculiar hyper-energetic events that are difficult to reconcile with spin down of neutron stars. And we have this peculiar, if you wish, orphan long GRBs that don't seem to have an association with massive stars or core collapse supernovae. So, what to make of it? So this brings me to the outline of my talk. I'll talk about progenitors of GRBs associated with rotating black holes. Radiation processes from frame dragging, so we'll talk a little bit about general relativity, and to probe the inner engine by time domain analysis to understand, basically what can we extract from the information we have today in electromagnetic radiation in the form of gamma rays, and then an outlook on long duration chirps from GRBs and core collapse supernovae. Okay, so we're looking at a complicated combination of phenomenology. And one of the ways to potentially make sense out of it is the following graph that looks at the sort of basic question, what might be the astronomical origin of long GRBs. Clearly, some of them are associated with core collapse supernovae. So if you wish, that's the easy part. And up to 2006, that was sort of a comfortable belief that many of us shared that kind of fixed, the origin of long GRBs. But in the SWEFT era, as you know, because of some of these events that don't seem to be associated with massive stars, that we created some doubt. And so in addition, what may happen if you associate long GRBs with rotating black holes with rapid spin, then of course you open a door to more progenitors. And one of the progenitors, interestingly, is of course a black hole neutron star merger. And Paczynski in 1991 already made some points in that direction. And if you allow the black hole to have a diversity in spin, because who knows how it was created, probably it was created by a prior supernova, then some of them, a fraction of them, may have high spin and hence may be associated with long GRBs. And a fraction of them may have low spin and may account for the short GRBs. But what is interesting, if you make this proposition, as I'll talk about, of associating long GRBs with black holes with rapid spin, then also neutron star coalescence comes into view, not as a progenitor of short GRBs as is commonly believed. I mean, the usual argument is actually short GRBs come from mergers, therefore all mergers produce short GRBs. Of course, that's not exactly, actually this is often stated quite widely, but not something you should be very proud of. Actually, it turns out when you look at neutron star coalescence, you can do, I'll show you a scaling argument, but also with high resolution numerical simulations at Max Planck by Boyotti et al. This actually produces a very rapidly rotating black hole. Not very high mass, obviously, but very rapidly rotating. And interestingly, you can put this in one expression. So take, for example, the merger of two neutron stars. Initially, of course, they evolved by gravitational radiation, just like the Hurst-Taylor pulsar has been evolving and will evolve for another few 100 million years. When they merge, you will produce a proton-neutron star that's not exactly a stable object, probably overheated, too much mass, and perhaps near a maximal rotation.
Maximal rotation, I've written this in '94. It's a very simple argument, and the maximal rotational energy that you have is much, much less than the rotation at maximal energy. It's a very simple argument, Newtonian argument, to see why when you merge two objects, the maximal rotation, the rotational energy is 1/4 of the maximal angular momentum.
Well, I'm first of all primarily concerned with the angular velocity. Is it larger than the angular velocity of the black hole that you make? The question is the angular velocity of that black hole larger than the angular velocity associated with its innermost stable circular orbit? That's the first question I'm concerned with. The second thing is the result I get from here is consistent with the numerical simulation of Boyotti in 2008. So I should certainly look at your paper to understand your argument, but I'm not familiar with it. So what I get here is consistent with the numerical results.
I don't know of any numerical result that can judge.
Yeah, Boyotti in 2008, very high resolution. They got A over M about 0.74 to 0.84.
No, the A over M is about is no larger than quarter.
A over M?
Yes.
They get definitely 0.74 to 0.84,
well,
depending on the equation of state.
It is independent of the equation of state.
Well,
the statement that I'm making is independent of the equation of state. It's very simple. I can explain it in 2 lines. Okay. Because at the moment that the objects are touching each other, they have maximal rotational energy, and each one is rotating around a mass of object M. So the angular momentum that they feel, that they need for the orbit, is the angular momentum of an object in a circular orbit with radius r around an object with mass m. Once they merge, they have the same total angular momentum, but the mass now goes to 2m.
2m? 3m? More like
no, the two masses are joined together. So you have, so the mass is now 2m. The mass is now 2m, and so the star so the outermost material is now rotating around an object which is twice as massive as it was rotating before. Therefore, the angular velocity that it has is much less than breakup angular velocity, and therefore the system is very far from breakup.
And why do they get numerically this 0.74?
Then I'm responsible for numerical errors of somebody else.
this initial, but then you can wait a while and you can redistribute the angular momentum by...
I'm talking about the total angular momentum that you have. It's trivial. The total angular momentum that you have available is just not sufficient for that. We can work it out in the break. It's a very simple argument. It's almost trivial.
Well, as I said, the key question here is actually, what is the angular velocity of the final black hole that you make? Is it larger than the angular velocity of the associated innermost stable circular orbit? For that, you don't need to be near maximal rotation. That's a little bit more subtle. You need a minimum A over m of 0.36.
Depends also on the mass. I mean, the specific angular momentum is one thing. The total one is a different thing. So, the question if you're referring to specific, to A or to the total.
I'm taking two objects that are rotating around each other with Keplerian motion, and they merge. And when they are dash touching each of the objects.
Oh, but they are not. Yeah, they are not really in Keplerian motion in the final plunge.
They are almost Keplerian motion. To very first approximation, they are Keplerian motion. If you now merge them, then you just do the calculation how much angular momentum you have in the system, and you discover that you are not near breakout. It's a very simple calculation.
Well, maybe the initial conditions by what they took are slightly different from yours.
It does not depend on the initial condition.
Well, we need to discuss this later. But as I said, the key question here is actually not only the rotational energy, but whether A over m is greater than 0.36 of the final black hole that you make. And if it's greater than 0.36, which is not a very strong requirement, then it falls into the category in my classification as a rapidly rotating black hole. Okay, if you do reach, or if the proton-neutron star is at breakup speed, okay, then you can write down, well, even if it's less, I mean, you can change the parameters in the formula, but then you would get about 0.4 solar mass in rotational energy. But as I said, the key parameter is actually A over m. So what I want to talk about is the potential for rotating black holes to make interesting radiation processes. And the agent to mediate this is frame dragging. And frame dragging has recently been measured by GPB and the Lagos 2 satellite. Of course, in a very non-relativistic limit around the Earth, where the angular velocity of the frame dragging is very small, is about 39 milli-arc seconds per year. Actually, if you put this in an astrophysical context, it's kind of like looking at the frame dragging angular velocity around a maximally spinning black hole with the same angular momentum as the Earth at a distance of 5 million Schwarzschild radii. So it's a very distant limit when you put this in astrophysical context, but it's a first principle experiment. Actually, these two experiments are essentially complementary because one is really on board a satellite and the other one looks at the frame dragging induced precession of the entire orbit in the Lagos satellites. Now, frame dragging is very pervasive. If you take a black hole and you ask what is a leading order approximation to frame dragging, it satisfies within about 7% this formula, that the frame dragging angular velocity, if you scale it to the angular velocity of the black hole, by definition, actually, incidentally, the frame dragging angular velocity is defined everywhere outside the black hole, and its limit on the event horizon defines the angular velocity of the black hole. So at large distances, it decays as 1 over the distance cubed, and in the vicinity of the black hole, this approximation holds pretty well. It's 1 over 1 plus the distance to the event horizon over 2m to the third power. And what the convenience of this approximation is that, as you can see, there is no colloidal angle dependence. It just depends on the radius to leading order. So frame dragging is everywhere. And frame dragging has various induced processes, both along the spin axis and in the equatorial plane. So along the spin axis, there are so-called Papapetru forces, which were identified in 1953, even before the Kerr metric. And it kind of changes this famous experiment in the so-called free-falling elevator a little bit. So in the original experiment, you're standing on a scale, maybe your weight is 170 pounds, and if the elevator is in free fall, okay, your weight will be 0, right? That's not exactly true because the Earth has an angular velocity and has an angular momentum. So if actually you're rotating with a positive angular momentum relative to infinity, for which you need to have at minimum the frame dragging angular velocity around the Earth, then actually you induce a spin-spin repelling force, the Papapetrou force, by which then when the elevator is free falling, it will appear as if you're moving up. So you better protect your head against touching the ceiling. Now this may look like a small force, and from a classical mechanics perspective, it is a very small force. But if you actually integrate this along the spin axis of a black hole, or along the spin axis of any rotating object really, you get that there is an associated potential energy that is the product of the frame dragging angular velocity and the total angular momentum of your test particle. Now ordinarily, the angular momentum of a test particle is very small in this context. But if it's a charged particle that is situated in an open magnetic flux tube, then of course the angular momentum of your charged particle is set by the flux associated with the choice of flux surface, and it need not be small at all. So let's have a look at what we might say that may be the immediate environment of a rotating black hole in an astrophysical context. So we have a rotating black hole with ingoing radiated boundary conditions. We have an accretion disk around it that is effectively ionized just like the surface of the sun, and will have Dirichlet boundary conditions. So a typical magnetic field line may look something like this, where it sort of stretches out and goes back into the surface, just like on the sun. Some of the field lines may break and may be open and produce open magnetic field lines to infinity, mediating perhaps some angular momentum and energy in a magnetic wind. There is also, because of frame dragging, a last field line, or a field line that is most extended towards the black hole but doesn't reach it because of frame dragging. Because of the Dirichlet boundary conditions, these field lines all have ab initio the angular velocity of the surrounding disk, and if the black hole spins faster than the disk, then this field line cannot, at least in the force-free condition, cannot reach the event horizon. So you make a bag that defines the maximal extent of such a force-free region towards the event horizon, but not allowed to touch it. If you do want to touch the event horizon of the black hole, associated with ingoing boundary conditions on the event horizon, while the same field line is subject to a Dirichlet boundary condition on the surface of the accretion disk, then you have something interesting. Because of the ingoing radiated boundary conditions, you have actually slip boundary conditions on the event horizon. So this field line is effectively rotating with the angular velocity of the disk. And so you can sort of complete this picture. And if you now allow the black hole to assume its lowest energy state, then actually it develops a finite magnetic moment that can readily support open magnetic field lines from infinity to infinity. The one infinity is on the event horizon, and one infinity is literally at infinity with outgoing. So basically you have outgoing radiated boundary conditions on one end and ingoing radiated boundary conditions on the other end. But frame dragging is very pervasive, as I was alluding to. It's everywhere in this picture. So frame dragging is along the spin axis, and of course it's also living about the equatorial plane. And the dependence on the poloidal angle is very weak. For all practical purposes, if we do an astrophysical calculation, you can neglect it. So it has radial dependence, but not very relevant angular dependence. So all of this now is subject, so this is way out of equilibrium. All of this is subject to energetic interactions. So there is one energetic interaction, this spin-spin Papapetrou force-induced potential energy along the spin axis, and there is the differential angular velocity between the black hole and the surrounding disk. So the black hole spins faster than the surrounding disk, which is this A over m greater than 0.36. Then you have you open a window to mediating transfer in a causal way, because it's mediated by frame dragging, feeding the surrounding matter by energy and angular momentum that actually normally we attribute. It's actually sitting in the entire surrounding space-time, but naively we attribute to the black hole. And the coupling strength of this is set by not by the poloidal field strength, but by the variance in the poloidal field strength. That will be important in what follows. Now, this is a very powerful interaction. In fact, by just topological arguments, it's not difficult to appreciate that most of the energy that is released in this process is actually put, if the black hole spins faster than the inner disk, is actually dumped into the surrounding matter. So the surrounding matter will be very hot. And of course, in this context, there are magnetic fields. It will also develop magnetic pressure. So there's thermal pressure and magnetic pressure. And quite generically, I mean, first of all, it certainly will induce forced turbulence. But because of this heating, you also tend to induce non-axisymmetric instability. And either by pure magnetic pressure, like Omer Bromberg in a paper we wrote together with Levinson a few years ago, alluded to, but also by generic Populus-Pringle instability. So the picture is much more dirty than I am giving here. It's much more messy and very time variable. The associated gravitational wave luminosity is not negligible. Even though, if you wish, the mass inhomogeneities that you might expect in a turbulent disk or by the non-axisymmetric instabilities to develop may be small relative to the mass of the black hole, because of the unit of gravitational radiation is, c to the 5th over g is so large, it's on the order of 10 to the 59. Even if you take a small fraction of that 10 to the 59, you readily look at 10 to the 51 ergs per second in this picture when, for instance, the surrounding disk is, say, 1% of the black hole mass, which is a very reasonable choice of parameter, and, say, the mass inhomogeneity you're looking at is, say, 10% of the mass of the inner disk. So what about the duration? So the proposition in associating long GRBs with rotating black holes is that the duration that we observe is the lifetime of the spin of the black hole. That's a very simple proposition. And of course, you can write down an equation expressing then the T90. So if you express it in units of 20 seconds, you can see the result here. Then, of course, the result depends on the ratio of the mass of the disk to the mass of the black hole. But essentially, what this is using is the notion that the total energy in the colloidal magnetic field is a fraction of the kinetic energy in the surrounding torus. That actually derives from an instability limit that, together with Levinson, we published in 2003. And it is consistent with numerical results, about 10%. So if you just look at the kinetic energy in rotation of such a disk, and you take 10%, and that's the maximum energy in the colloidal magnetic field that that disk can support before the colloidal magnetic flux becomes unstable. And as you can see, there is also an m squared dependence that comes out. So basically, it's m over the mass of the black hole over the mass in the disk times the mass of the black hole. So if you take the mass of the disk, for instance, to be a constant fraction in your sample of GRBs relative to the mass of the black hole, then you will find a positive correlation between the kinetic energy in the supernova and the true energy in gamma rays if you associate the winds coming from the disk, being, of course, fed by the energy from the black hole, as providing the input to the supernova. On the other hand, if you imagine, perhaps in some exceptional cases, maybe a GRB from a 100 solar mass progenitor, you form a very high mass black hole, and at the same time perhaps a very low mass disk because the density might be somewhat lower than normal, then you get a T90 that's like an hour. So the rest of my talk will be about testing this model. So one test you can do is to look at this E is omega j ab initio interaction to launch high energy emission along the spin axis. Actually, this introduces in combination with this proposition that the lifetime of the spin sets the duration of the burst, it actually sets a correlation between the peak energy in the internal shock model and the duration of the burst, which is representative for the magnetic field strength in the inner engine, and the true energy in gamma rays. So in 2004, I was able to do some statistics with then 25 events that had estimates for E gamma. And you find that adding the T90, so this actually is a model-generated correlation. This is not a trial and error correlation. You find that adding this T90 to the 1/2 improves on the G-lambda relation. So just to summarize so far, if you ask the question, what prospects can black hole inner engines give versus neutron star inner engines, you find that the black hole torus systems have some advantages. It's not only the energy, the total energy and spin of the black hole that is enormously large compared to the maximal spin energy in a neutron star, But of course, the black hole torus system has the advantage of being able to produce two winds at the same time, a baryon-rich disk wind and a baryon-poor wind coming from the black hole. And baryon-rich winds are great for making efficient supernovae. And of course, baryon-poor jets are great for making GRBs. Whereas if you look at, say, the spin-down process of a perhaps proton-neutron star making a similar event, then you're looking at making a supernova in a GRB from one wind, one object, one source of the magnetic wind. And so either you make a successful GRB, but then your wind will be very baryon-poor and not make a great supernova, or you make a great supernova, but perhaps not a very good GRB, apart from the fact that you're energy limited. So to test this, in trying to extract what we call electromagnetic priors to search for gravitational waves, let's pursue two studies in the time domain. One is on the T90. So in this model, the lifetime of the spin is set by the spin down time of the black hole. So you expect, because of this interaction between the black hole and the surrounding matter, the black hole to gradually spin down over the duration of the GRB, so on the order of tens of seconds. So one way to do this is to use match filtering. So what you want to do is to extract a normalized light curve from an unbiased set of long GRBs. Of course, then we turn to the Betsy catalog, which had 1,491 light curves of long GRBs. And before you do your averaging, it's a little tricky because these light curves are very messy. So you want to have a stable averaging process, i.e. you want to have a stable normalization of each light curve in time and in count rate. Say you want to set the time over a fixed window of normalized time and the count rate, say, from 0 to 1 or 0 to 100%. And the way to do that is use match filtering. So that then involves 4 parameters. You shift the light curve, because we're only interested in the shape of the light curve, so you shift it in time, you shift it vertically, and of course you scale it in time and you scale it in count rate. So you can do this thanks to the Betsy catalog. This is all of them, incidentally, 1,491. They're all scaled here and also ordered by T90. So left top is 3 seconds and top down is 1,407 seconds. So you can average these things if you do this in a proper way. So once you calculate your normalized light curve, you want to compare your normalized light curve with your favorite model. That's the idea of match filtering. You can choose any model that you can dream up with and then make a test against these data. So we chose 3 models. One is spin down against matter at the ISCO. That seems the most natural choice in this context. The other one is fairly arbitrarily to choose spin down against matter further out. Matter further out has an angular velocity which is smaller. For instance, you can choose a torus angular velocity that is, say, 1/2 of the angular velocity of the black hole. It's a completely arbitrary choice. Just make sure you have something which is distinct from the angular velocity at the ISCO. And of course, C, the third choice, is a light curve that represents spin down of a neutron star. So the result you get is as follows. So the thick line, as you can see in these 6 windows, is the normalized light curve of GRBs. And here we made a separation. We made a partitioning of the 1,491 into intermediate duration long GRBs, i.e. from 2 seconds to 20 seconds. And then we also made on the right a group of GRBs that have very long duration, all of them more than 20 seconds. And the thin line is the model light curve. So here you see the model light curve for a neutron star spin down. And in the other pictures, you see in the thin lines, the model light curves for spin down against the ISCO and spin down against matter further out. So what you find is that the fit is reasonable but not perfect in this group of 2 seconds to 20 seconds, but the fit becomes better if you go to very long duration. And that's because here in this, or we attribute this to the notion that here our template light curve is one of an initially maximally spinning black hole. And the other templates, as you can see, have a fit which is notably less good, at least on average. This is not to say that some of the light curves, that none of the light curves have a good fit to the neutron star light curve. That's not true. There are actually a few events which actually match remarkably well. But of course, here we are looking at averages. So on average, the winner is the very long duration ones, that describes spin down of an initially maximally spinning black hole against matter at the ISCO. Now you can go further, and this was the main topic in the last 3 minutes of my talk. This inner engine is very intermittent because the state of matter that you introduce is in forced turbulence. And the coupling between, or the GRB derives from this E is omega J, where J is the angular momentum of particles in the magnetic flux supported by the magnetic moment of the black hole. And of course, all of this is induced by the colloidal magnetic field in the surrounding matter. So the surrounding matter is intermittent, and the jet will also be very intermittent because of this variance coupling in the colloidal magnetic field. In addition, the jets that we see may be modulated by collimating disk winds. I mean, they are probably collimated by disk winds, and those disk winds may be intermittent in their own right. You can think of precession, but you can also think of much more higher frequency types of instabilities. Now, in order to address intermittencies, we turn to the Beppel-Sachs catalog. So here is a selection of 72 events of relatively bright long GRBs from the 1081 in the full Beppel-Sachs catalog. So these are sampled for the first 8 seconds at a sampling rate of 2 kilohertz. Now it turns out if you perform a autocorrelation analysis of these 72 bursts, you find that many of them have a trivial autocorrelation function. And the majority of them have a non-trivial autocorrelation function. So I call them white and red. And then, as you know, the Fourier transform of your data is simply Fourier transform of the Fourier transform of the data squared gives you the autocorrelation function. So you can also plot the same result in the Fourier domain. So you find that the red bursts, which have a non-trivial autocorrelation function, have this kind of Fourier spectrum where vertically is the Fourier coefficient. So it's not Fourier coefficient squared, which would give you the power, but I chose here the CK. This result is very typical. You get a minus 0.814. So if you multiply this by 2, you get the usual 5/3 of a Kolmogorov spectrum, and that was already seen this is my own picture, but by earlier studies by Bela-Borodov on the Betsy catalog. So this is a known result that at very low frequency, you get the 5/3 law. So we see that here too. But here we see in the Beppel-Sachs catalog actually a second group, the white bursts. So not all of them have this feature. But of course, if we really want to learn about the inner engine, we want to go much further than the 10 Hertz cutoff that effectively we are looking at here using pure Fourier. So Fourier doesn't get you very far. So what we... Yeah, if you square it. Yeah, this is a square root. So this is a completely familiar result, except for in the Beppel-Sachs case that you get 2 groups, which is apparently hasn't been observed before. And I don't know what it means at this point. I just make the observation. But if you want to go further, you have to do an entirely different analysis. You cannot use Fourier. So we want to go further than what Fourier can give you. So we use chirps. So chirps extend Fourier with 1 dimension, which is the rate of change of frequency. This is a messy inner engine. I didn't expect and didn't find, and no one found, in fact, QPOs in these events, as you know. There are a few papers about it. Most of them confirm that, we don't see anything. So to go further, we look at unsteady frequencies that have a secularity to it, which is a rate of change of frequency. So you can think of, say, positive chirps and negative chirps. So what I did was having a model for a black hole spin down. You chop it up in time slices. This is something we developed for Cachra. For gravitational wave analysis, but ultimately this is the same method you can apply to gamma rays, and of course ultimately vice versa. So you slice it into small pieces in the hope that there is an intermediate time scale during which the inner engine behaves more or less in a deterministic fashion. It definitely will not behave in a deterministic fashion over the entire duration of the burst, but maybe over 100 orbital periods you may have a slightly coherent frequency. And all of this you will only discover to be correct or not after the numerical analysis. Now, because at this point I'm not going to distinguish between positive and negative chirps, I'll just take the difference. So you can think of, say, matter further out in the disk that may have a positive chirp because it's slowly migrating towards the inner engine. Matter near the ISCO will have a negative chirp because of the spin down of the black hole. The ISCO will expand, and so the frequencies will slowly decrease. And turbulence, who knows, may make both signs at any radius. So we took a differential chirp. And what you do then is, well, you calculate, there's sort of more or less standard recipe, a sample correlation coefficient, then you calculate the maximum of the sample correlation coefficient over the entire shift through your data. But very important, you need controls. So the control I took was double. I took a control such that by using each Beppel-Sachs light curve following a randomization in time that kills all temporal information. The second control was independently a light curve that is generated by a random number generator. Just take a photon count between 0 and 1 or 0 and whatever you choose. And then we want to calculate the normalized spectra. So I define here delta to be this maximum minus the maximum from the control over the maximum of the control. So this is a dimensionless output. And you can actually compare this to the Fourier spectrum I just showed by also normalizing in a similar fashion the Fourier coefficients. So at the end of the day, I'm going to compare normalized, i.e. dimensionless Fourier coefficients with dimensionless deltas I showed here. Now this is not cheap. So we did here a full-blown search over 35 million chirp templates over 72 Beppel-Sachs light curves. Okay, that takes about a week on a supercomputer with 256 nodes. And this is what you get for the... So what is interesting is that if we look at the white bursts that were very boring in the autocorrelation function and relatively boring also in the Fourier spectrum, you find that they continue to be white following the chirp analysis. But of course here, now we're going up to 1 kilohertz. But the red bursts, which were non-trivial in the autocorrelation, non-trivial in their Fourier spectrum, are also non-trivial in their chirp spectrum. And this is averaged over all the 42 red bursts, and this is averaged over all 30 white bursts. You can, and I should say this was done with a tau, an intermediate time scale of 1 second. So we had 8 segments, each of 1 second. Ideally, we would have taken 10 segments, but not all of the Beppel-Sachs light curves as advertised were sampled for the first 10 seconds. So they were all sampled, there were a few exceptions, they were all sampled for 8 seconds. So that's why I chose 8 rather than 10 to do everything uniformly. You can actually normalize it to co-moving frequency for this choice of tau, and then you find that there is a well-defined, you can derive a well-defined slope in this region. It turns out, this is work in progress, that this slope is not stable to the choice of tau, which may well be a physical reason behind it, nor is this slope stable to the choice of tau. But this slope, up to about 350 hertz, is stable with respect to the choice of tau. And as you can see, well, I mean, I didn't do any slope analysis on the white burst because delta is very, even in the co-moving analysis, this is very low in strength. So what you find here is that this compares well, this break, with what you might expect from the chirps associated with the mass inhomogeneity sitting at the ISCO for an m equals 1 instability. You get about 350 hertz from the theoretical value for a mean black hole mass of 10. Of course, if you translate this to gravitational waves, you have to multiply this frequency by 2. Okay, I'm almost done. 1 more, 2 more. Okay, so just to show you side by side, so these are normalized Fourier spectra, otherwise you cannot compare. Of course, you want to compare apples with apples, not have something dimensionful and dimensionless. So this is dimensionless. So this is the picture I already showed you, but now I've added the chirp spectrum. I also had to multiply it by 10 because this is a very small signal. It's very well resolved, but it's very small. So you can clearly see that, Fourier gives no information further than 10 hertz, but the chirp spectrum gives you information, at least for the red burst, a non-trivial signal up to 1 kilohertz. And so just to wrap it up, so the long GRBs give a telltale of relativistic frame dragging playing itself out around rotating black holes surrounded by hot and high density matter. And essentially the key parameters are listed here, the T90 being identified with the lifetime of spin, high energy emissions associated from this potential energy derived from the pop-up force, a typical gravitational wave energy output of on the order of 0.1 solar masses, and a sensitivity distance that we developed against chirp, using a chirp analysis on the TAMA 300 data of about 35 megaparsec. And because of time, I'll not say too many words on this one, but you can actually put everything in a graph like this, which shows you the prospect for gravitational wave emission from mergers and core collapse supernovae in the same plot, where of course the mergers give you positive chirps and the spin down of black holes associated with supernovae and mergers that are associated in their own right with rapidly rotating black holes give you negative chirps. And then the frequencies you get are simply twice the frequencies I just showed you, because the minimum emission in gravitational waves comes from the quadrupole moment. So the outlook, that is in terms of what might we wish to do to pursue these signatures, is a multi-messenger chirp search. You want to do your chirp search in the electromagnetic spectrum, in this case, of course, gamma rays, as being most directly connected to the inner engine, as well as, of course, chirp search also in gravitational waves. And you should find consistencies. And one consistency is that the duration that you may find in your gravitational wave burst should mimic the duration that we are already familiar with in the gamma rays from the GRBs. So it's really up to, for instance, developing a complete optical radio survey of the nearby core collapse supernovae. And it's also up to developing very high performance computing infrastructure to do the actual analysis. I actually did one test on the TAMA data, and it took me just for 13 seconds of analysis, because it's sampled at 20 kilohertz, not 2 kilohertz. I downsampled it to 10 kilohertz, but even then it takes like a week on 256 computers to analyze 13 seconds of data. So this is not enough. You also need some really good supercomputing equipment. Thanks for the time.
Thank you.